Today, we are digging into a really cool new idea in AI. It's a way to get models that are smarter, faster, and believe it or not, cheaper to run. It's called Mixture of Recursions, or MO-hour for short, and it's all about trading brute force for, well, a little more brain. So let's just start with the big question that's on everyone's mind. You hear it all the time, right? AI models are getting bigger and bigger, scaling up to trillions of parameters. But are they hitting a wall? Because the truth is, the way we've been building them is becoming unsustainable. The costs, we're talking computational power, money, and even environmental impact, are just staggering. And that brings us right to our first topic, the AI efficiency wall. This is the fundamental problem, the big hurdle that this whole mixture of recursions idea was created to overcome. Okay, so when we say brute force, what do we really mean? Well, the best way to picture it is to think of a traditional AI model, the vanilla transformers behind most of today's big language models, as this gigantic, mile-long assembly line. Now imagine every single piece of a problem, every single word, has to go down the entire line. It gets processed at every single station. It doesn't matter if the word is something simple like and or the, or a really complex idea. Everything gets the same exhaustive and, frankly, wasteful treatment. And as you can probably guess, running an assembly line like that has some serious consequences. We're talking about an absolutely enormous computational cost. That in turn creates a massive memory footprint and, you guessed it, incredibly high energy consumption. It all adds up to one thing. These models are just wildly expensive to train and even more expensive to run for people like you and me. It's just not a path we can stay on forever. So if the bigger is better philosophy is running into a wall, what's the alternative? Well, that leads us right to the core philosophy behind MAR. The goal here is to be smarter, not bigger. And here's where things get really interesting. Instead of that huge, rigid assembly line, I want you to imagine MORE as a small, elite team of multi-talented geniuses. Now this team, it only re-examines a problem as many times as it needs to. Simple stuff gets a quick glance. The really tough, complex parts, they get more focus, more brain power from that exact same small team. You see? You don't need to build a bigger factory. You just need a smarter, more flexible team. Now, this whole smarter team approach, it has a technical name, adaptive computation. But don't let the jargon fool you. The idea is incredibly intuitive. This is the absolute key. Instead of just throwing the same massive amount of processing power at every single thing, the model learns to think harder on the tricky parts and just breeze through the easy stuff. It adapts its effort depending on how hard the problem is. All right, so this elite team sounds great in theory, but how does it actually work under the hood? So let's go inside the MAR engine and see what makes this whole adaptive thinking thing possible. It really all boils down to three key ingredients. First up is parameter sharing. This is the elite team. It's one small set of AI layers, or parameters, that gets used again and again. Second, you have dynamic routing. This is the smart manager, the one who decides what the team should focus on and for how long. And third, efficient KV caching. Just think of this as the team's shared notepad, but one that's been brilliantly optimized to save a ton of space. Let's really zero in on that manager for a second, the dynamic routing. This is the real secret sauce. At the heart of the MOR model is this little component called a router. Its one job is to look at every piece of information, what AI folks call a token, and decide how many times the elite team needs to process it. In the paper, this is called assigning a recursion depth, and all that means is how many times do we need to think about this? More recursion just means more thinking. Simple as that. Now, what's really clever is that this manager has a couple of different ways it can hand out assignments. On one hand, you have expert choice routing. Here, at each step of the thinking process, the manager is basically saying, okay, team, for this next go-around, I want you to focus only on these specific tricky words. Then, on the other hand, you have token choice routing, and this is different. Here, the manager looks at every word right from the start and assigns its whole journey, saying, you're complicated, you get 3 rounds of thinking, and you're easy, you only need 1. So this smarter way of routing the work, it isn't just a cool concept. It has a massive, and I mean massive, measurable impact. And that brings us to the math of efficiency. But before we get to the amazing numbers, we need to quickly talk about one more thing, the KV cache. The easiest way to think of this is as the AI's short-term memory, or its scratchpad. When you're chatting with an AI, it uses this cache to remember the context of the conversation. That way, it doesn't have to reread everything from the beginning for every single new word you type. It's crucial for speed, but in normal AIs, oh my gosh, it is a major memory hog. And this right here is where MoR performs its magic. Now, don't worry about the formulas on screen. You don't need to memorize them. The only thing you need to take away is that Mo has two incredibly clever tricks to shrink that memory-hogging KV cache. The first one basically creates a tiny new notepad for each round of thinking. The second one, recursive sharing, is even slicker. It just uses one single notepad from the very first round and shares it for all the other thinking steps. So what does all that fancy math actually translate to in the real world? This, 67%. By using that recursive sharing strategy with just 3 rounds of thinking, the amount of memory needed for that short-term cache is cut by 2/3. Let that sink in. That is a 67% reduction in one of the biggest bottlenecks holding AI back. It's a massive, massive saving. So, okay. It's cheaper, it's way more memory efficient. That's great. But here's the million-dollar question. Is it actually better? Does it perform as well? That brings us to our final section, where we see the proof that it delivers better performance for less cost. And I think the researchers themselves said it best, so I want to start with this quote directly from the paper. They say, MAR forms a new Pareto frontier, an effective path towards large model quality without incurring large model cost. Now, Pareto frontier sounds super academic, right? But all it means is that you are getting the absolute best bang for your buck. You literally cannot get better performance for the same cost, or the same performance for less cost. It's the new gold standard of efficiency. And the data completely backs this up. Just take a look at this chart. All you need to know is that this is measuring performance, and a lower bar is better. So what do you see? The more models are right there with, and in some cases even beating the standard models, all while using a much smaller compute budget. It is quite literally doing more with less. And this isn't just about training costs behind the scenes. This is about speed for you, the person using it. Inference throughput is just a fancy way of saying how fast the AI can generate an answer. And on this chart, higher is better. As you can plainly see, the MoR models are significantly faster. We're talking up to twice as fast. So not only is it cheaper to build, it's actually faster to use. So let's just pull this all together. The payoff here, the reason this mixture of recursions idea is such a big deal, is huge. First, it's cheaper, which means lower cost for training and running these powerful AIs. It's faster, giving us answers more quickly. It's more accessible, which could mean that world-class AI quality is no longer just for companies with giant data centers. And maybe the most important part, it's scalable. This isn't just a one-time trick. These efficiency gains keep working even as models get bigger and more powerful. Which kind of leaves us with one final, pretty mind-bending thought. We've just seen an AI that's not just learning a task, it's learning how to do that task more efficiently. It's learning how to focus its own thinking. So it really makes you wonder, if an AI can learn a human habit like being efficient with its resources, what's the next human habit it's going to pick up?